This is lesson 3. We're going to look at comparison of series using 2 different tests today. We're going to talk about the direct comparison test and the limit comparison test. These new tests will allow us to compare a complicated series with a simpler series. And we need to be aware that the terms in the series have to be positive term series. So let's jump in with our first example. In the direct comparison test, if we let a sub n be 1 over 2 to the n and b sub n be 1 over 2 to the n plus 1, we want to write out the first 5 terms of each series. So this one would be 1/2, and when n is 2, we have 1/4. I'm looking at a sub n. And when n is 3, when n is 4, and then when n is 5. So in b sub n, we have n is 1, and n is 2, n is 3, we have a 9th, and then when n is 4, it's 1/17, and finally 1/33. To complete the statement with less than or equal, greater than or equal to, we could say that the series a sub n is going to be greater than or equal to the series b sub n for all values for n greater than or equal to 1, because 1/2 is greater than 1/3, and 1/4 is greater than 1/5, and so on. Notice that a sub n is a geometric series, and if we wanted to find the sum would be the first term divided by 1 minus the ratio. So the sum is 1. We're using that formula for geometric series. A sub 1 divided by 1 over r is the sum of the series. In step 5, using your findings from questions 3 and 4, what can you conclude about the series, the sum of the series from 1 to infinity on the b sub n term? Well, looking back, I could say that the series from 1 to infinity for b sub n is going to be less than 1 because each value is smaller. Each value is smaller than the a sub n values. So I would say that it would be less than 1. Verbally speaking, if you think the series converges, we can compare it to a converging series. And the series you compare it to should be a larger series. But if you think the series diverges, you can compare your series to a diverging series, and the series you compare it to should be smaller. So stating that test verbally, we could say, suppose you have some series a sub n and b sub n, and all the series are positive terms. Then if a sub n is smaller than b sub n, but a sub n is greater than 0 for all of your n values, if b sub n converges, then a sub n converges. That's basically saying if the larger series converges, then the smaller series converges. And likewise, if a sub n diverges, then b sub n diverges. So if the smaller series is divergent, then the larger series is divergent. Or I'm saying that a is smaller than b. So let's determine whether the following series converge or diverge. In example A, we're going to compare this to 1 over n to the 1/3 power. So let's use the smaller value, 1 over n to the 1/3 power, because this is my smaller one. And 7 over n to the 1/3 is going to be greater than 1 over n to the 1/3 for all n greater than 1. That tells me that the summation, or the series, n over 1/3 is going to diverge because 1/3 is less than 1. So this smaller series is going to diverge, and our larger series also diverges. So you can see what we did. We saw that this was a large series, and we picked a smaller series. So this one is larger than this one, and this smaller one is going to diverge, which means that so will my larger series also diverge. Okay, let's look at part B here. We have 2 to the n over 1 plus 3 to the n. And as n goes from 1 to infinity, adding 1 to infinity doesn't really do a lot to the summation. So let's think about comparing our series in part B. We'll compare it to 2 over 3 to the n power. Now this is a geometric series, and we know 2 to the n over 1 plus 3 to the n is going to be less than 2 over 3 to the n for all n greater than 1. So the series from 1 to infinity of 2 over 3 to the n will converge. And the reason we know that is because our geometric series is our ratio is less than 1. So our smaller series, n going from 1 to infinity of 2 to the n over 1 plus 3 to the n will also converge. So this is a convergent series. In part C, we have the summation from 1 to infinity of n minus 1 over n cubed plus 3. And we're thinking about that in behavior. So when you're thinking about those large numbers as we approach infinity, you can think about this in behavior model. This becomes, dividing every term by n cubed, this becomes 1 over n squared, and this becomes 1 over 1. So we got 1 over n squared would be the series we could compare for part C. And I want to make sure that how my terms are, who's bigger and who's smaller. So if we say a sub n and we substitute this one as our a sub n, let's call this one a sub n, and this one we'll call b sub n. So 1 minus 1 is 0. Our first term is 0. And then 2 minus 1 over 2 cubed, that's 8, plus 3, that's 11. And then 3 minus 1 makes 2 in the numerator, and 3 cubed plus 3, and then 4 in the numerator is 3, or 4 minus 1 is 3, and 4 cubed plus 1 is 37. And then our b sub n, this is 1 over 1, and then 1 over 2 squared, and 1 over 3 squared, and then 1 over 4 squared. So looking at this progression, we have positive numbers, and a sub n is less than b sub n for all of our values greater than or equal to 1. That tells us a sub n converges because b sub n converges. We saw that in our last lesson, 1 over n squared, the p-series test. In part D, sort of the same thing, 8n squared plus 1 at infinity plus 1 doesn't do anything. 2n cubed minus 1 won't affect infinity. So we could think about comparing n squared over n cubed, and that would simplify down to 1 over n. But if this is going to be our b sub n, or this is our a sub n, this is going to be our b sub n. But b sub n is the harmonic series. And we saw when p was less than or equal to 1, in this case it's equal to 1. And if we compare our a sub n terms to our b sub n terms, we know that the b sub n terms are 1 and 1/2 and 1/4 and so forth. And our a sub n terms would be 8 over 1 and, do a little math here, 33 over 15. And then when n is 3, that's 9 times 8, that's 76. And 1 is 77 over 53, I believe. So a sub n. Looks like a sub n is bigger than b sub n for all of our n's greater than or equal to 1. And that tells me that a sub n is going to diverge because b sub n is a divergent harmonic series. So a sub n is going to diverge because we know from our last lesson that b sub n was a divergent series. So here's an exploration. Can the direct comparison test fail? If we let a sub n be 1 over 2 to the n minus 1 and b sub n be 1 over 2 to the n, we want to write out the first 5 terms of each of the series. So in the first one, the first term would be 1. And then when n is 2, that would be 1/3. When n is 3, that would be 1/7. And then 1/15 and 1/32. In the b sub n, we have 1/2 plus 1/4, and then 1/8, and then 1/16, and finally 1/32. So what do you notice about the terms of each series? It looks like the a sub n terms are greater than the b sub n terms. And will the series converge? Well, you can't really be sure because as we get out here, they're kind of similar, aren't they? So this is a not really sure. The terms are similar. So it may converge or it may not. May or may not converge. So we can't really tell just by looking at those first few n terms. Here are the limit comparison test. This is our last test in this lesson. Suppose that you have the series a sub n and b sub n and their series with positive terms for all of our n values, where n goes from 1, 2, 3, so on and so forth. We can say if the limit as n approaches infinity of the ratio of a sub n over b sub n is a positive finite number, then either both series converge or both series diverge. So we want our values to be positive and finite. This test is a great tool for comparing a lot of messy algebraic series with a p-series. Just beware that you have to choose a p-series with an nth term of the same magnitude as the messy series that you're considering. For example, if we have this messy looking series, we want to consider the p-series with n squared because our highest agreed term is there. You only need to consider the highest powers of n in the numerator and the denominator. So let's try a few of those. Here we want to apply the limit comparison test to 2 over n cubed plus 4. So if this is our a sub n, we want to look at our b sub n to be 1 over n cubed. And we know b sub n converges, but it's less than a sub n. So we can't really use the direct comparison test. You might want to write that down. We know b sub n converges, but b sub n is less than a sub n. And because of that, we can't use the direct comparison test. But we can use the limit test. So here's how the limit test works. We want to take the limit as n approaches infinity of 2 over n cubed plus 4, and we want to divide that by 1 over n cubed. Now, what happens to all of that? The limit as n approaches infinity of 2 over n cubed plus 4 times n cubed over 1. At infinity, this is gone, and adding 4 times 1, that doesn't really matter. So our limit as the comparison test here, the limit comparison test, approaches infinity, we're approaching 2. So b sub n, we know b sub n is a convergent p-series because our power is 3. It's greater than 1. That tells us, let me get a little more room to write here. If I just rewrite this, we know that the limit as n approaches infinity of a sub n over b sub n is 2. And 2 is between 0 and infinity. So it's positive. The limit is positive, and it's finite since the limit is 2. Therefore, by the limit comparison test, both series converge. And if you need to, you might want to write down, we know that b sub n is a convergent p-series where p was greater than 1. And then we have one more to go. So applying the limit comparison test, this is something messy, and we want to compare this, our b sub n, to n to the 4th over n to the 5th, which will be 1 over n. And what do we know about 1 over n? This is a divergent p-series, or what we're calling the harmonic series. So we want to use the limit comparison test, and that says the limit as n approaches infinity of our a sub n, so n to the 4th plus 5 over 4n to the 5th minus 2n cubed plus 3, messy. We're going to divide it by 1 over n, so I'm going to go ahead and show the multiplying by the reciprocal. The limit as n approaches infinity will be n to the 5th plus 5n over 4n to the 5th minus 2n cubed plus 3. And as n goes to infinity, all of this stuff at infinity doesn't matter, and we get 1/4. So it's finite and positive. Our limit is finite and positive. It's between 0 and infinity. Therefore, by the limit comparison test, the limit as n approaches infinity, comparing a sub n to b sub n, is 1/4. It's finite and positive. So both of our series diverge. And that's the end of lesson 3. We'll talk about alternating series next time.